Having discussed center of shape, we now turn to center of mass and center of gravity. As mentioned in the previous section, we won't examine any problems where there is a gravity gradient through an object, so there will be no distinction between center of mass and center of gravity. But there are two important classes of problems where there can be a difference between center of mass and center of shape. First, mass densities can be described in different ways depending on the object. Fundamentally, mass density is a mass per unit volume, but if the object has one or more dimensions that are small compared to its other dimensions, the mass density can be specified in different ways. Sheet metal, for instance, has a thickness that is very small compared to its lateral dimensions. The mass density for sheet metal might be described as an areal mass density. Rho sub A is the product of volumetric mass density rho times thickness T. The thickness is embedded in the areal mass density, and we say that the mass of the sheet metal is its surface area times its areal mass density. In the same way, wire has a length that is long compared to its lateral dimensions. If this is a circular wire of diameter d, we would say that d is much, much less than L. The mass density of the wire might be described as a linear mass density, rho sub L, equals volumetric mass density times the wire's cross-sectional area. If it's a circular wire, that area would be pi over 4 d squared. The cross-sectional area of the wire is embedded in its linear mass density, and we say that the mass of the wire is its length times its linear mass density. Because we are calculating a center of mass, we can mix volume, area, and line segments as long as these are weighted by the volumetric, areal, and linear mass densities respectively. The center of mass is the mass-weighted average of the centers of all constituents making up the assembly. If the object is a composite of elements of disparate size, with mass densities described as a mix of volumetric, areal, and linear mass densities, then the center of mass calculation looks like this. The center of gravity is the force-weighted average of the centers of all constituents making up the assembly. Note that we can replace the specific weight symbols, the gammas, with products of volumetric, areal, or linear mass density times little g. For uniform g, the g cancels in the numerator and denominator, and there is no distinction between center of mass and center of gravity. A second application, where there is a distinction between center of shape and center of mass, is shown here. Materials are not required to be homogeneous, that is, they are not required to have constant mass density. If an object has a gradient in its mass density, its center of shape and center of mass will not be the same. An excellent example of this is shown in example 7.9 in your textbook. In that example, a functionally graded material is present in a conical shape. Recall that the centroid of a cone is 1/4 of the height from its base, or 3/4 of the height from its tip. For the specific conditions of example 7.9, you will see that although the center of shape is 75% of the conical height as measured from the tip, the center of mass is 72% of the same distance. The two centers are not the same. Now let's take a look at some examples. In this first example, we have the rudder of a small boat that consists of three elements: a stainless steel shaft, which is given as a volumetric element, a brass plate, which is given as an areal element, and a stainless steel wire, which is given as a linear element. And their corresponding specific weights are shown here. We're asked to find the weight of the rudder and the y position of its center of gravity, given the coordinate system shown in the figure. The brass plate is semicircular, as is the stainless steel wire, and we could use tabulated values from our textbook to find the centroids of those quantities. For a semicircular line, the centroid is 2r over pi from the semicircular diameter. For a semicircular plane, the centroid is 4r over 3 pi from the semicircular diameter. One other thing for us to note for both the line and the plane is that we have to add the radius of the solid cylinder, since the semicircles are offset by that amount. I will call the solid cylinder 1, the brass plate 2, and the stainless steel wire 3 in the calculations below. For the solid cylinder, we have that y1 is equal to 0. For the brass plate, we have that this is equal to the radius of the cylinder plus 4 times the radius of the plate over 3 pi. That's 0.4 inches plus 4 times 6 inches over 3 pi. And that number ends up being 2.946 inches. For the center of the stainless steel wire, we're again adding the radius of the solid cylinder as an offset, plus now 2 times the radius of the wire over pi. And that's 0.4 inches plus 2 times 6 inches over pi. And that number turns out to be 4.22 inches. The corresponding weights of each of these are the specific weight of the cylinder times its volume, which is pi times the radius of the cylinder squared times the height of the cylinder. That's 0.284 pounds per inches cubed times pi 0.4 inches squared times 14 inches, and that number turns out to be equal to 1.999 pounds. For the brass plate, we have the areal weight density of the plate times its area, which is just half of a circle, so it's 1/2 pi times the radius of the plate squared. That gives us 0.04 pounds per inches squared times 1/2 pi 6 inches squared, and that number turns out to be equal to 2.262 pounds. And finally, for the wire, we have the linear specific weight of the wire times its length, which is just half a circumference. So we have 0.15 pounds per inch times pi times 6 inches, and that number turns out to be equal to 2.827 pounds. The center of gravity is just the force-weighted average of the positions of those individual pieces. So this ends up being 1.999 pounds times 0 inches plus 2.262 pounds times 2.946 inches plus 2.827 pounds times 4.22 inches. And in the denominator, we have the sum of the weights. The result is that we have a numerator of 18.594 inch-pounds over a weight of 7.088 pounds, and that gives us a Y center of 2.62 inches. So our weight is here, and our Y center is here.